Okay, here are 6 essay questions, potential essay questions, or variations on them. I'm not necessarily just going to pick these, but this is what I sketched out as a good place for you to study. So we're trying to push our understanding past just being able to do calculations and choose the right formula and multiple choice questions. We really want to have a broad understanding of the terms and concepts and relationships that we're learning. And so writing essay questions pushes us past that limit. And so we're going to practice that on the quizzes in preparation for the final exam, being able to express our understanding of terms and concepts. I use those interchangeably, right? Term or concept. Terms and concepts have definitions. Physical concepts usually have units. And so we want to understand the terms and concepts such as electric field, magnetic field, electric potential. And then we have relationships. That's like Gauss's law or Coulomb's law. Relationships. That's relationships between terms and concepts. And sometimes those things are physical laws, like the law of conservation of energy, the law of conservation of momentum. Okay, so look over the set of questions and I'll discuss each one of them with you in preparation for Quiz 9 on magnetism and magnetic fields. So question 1, the single unifying concept throughout the entire semester, fundamental basic concept for science and engineering, is the concept of field. And the short quick answer is field refers to space, right? So a soccer field is a space in which you play soccer. We have scalar and vector fields. The temperature field are the temperatures mapped throughout space. That would be like a temperature map. Pressure fields, the pressure map of the country or some area. A time field, that would be the times at various places across the globe. That would be a time field. The density field, the density at all points in the Earth. That would describe the density field of the Earth. And in terms of vector fields, velocity, like wind velocity, magnitude and direction across a map. For our purposes, this semester we're studying the electric and magnetic field, and last semester we studied the gravitational field. And so the electric and magnetic field are the strength of the electric and magnetic field at any point in space, and they are vector fields. And the electric field has units of newtons per coulomb, and the magnetic field has its own particular unit, which is a complicated mixture of subunits called T, or the Tesla. That's the unit of magnetic field. Okay, question 2 and question 6 are basically the same question. So electric field has a very compact definition, or a specific definition that we refer to often. It's the force per unit charge at any point in space. The direction of the electric field is the direction of the force on a positive charge. If the charge is negative, the field will point opposite the direction of the force on a negative charge. Similarly, the definition of magnetic field would be the force per unit of wire length, but it's a cross product, so it's a little bit more complicated than the electric field. It's L cross B, so they have to have the sign of theta in there. or it's the force per unit charge, but the charge has to be moving. So whereas the source of all electric field lines are positive and negative charges, and field lines always begin or start on a positive charge and end on a negative charge. In contrast, magnetic field lines have no beginning, no end. They're closed loops. There are no magnetic monopoles. There's no isolated north or south pole. So all magnets are dipoles. And so the way we detect an electric field is to put a charge in the field and see the direction of the force. Whereas detecting a magnetic field means putting a small magnetic dipole, like a compass needle or an iron filing that becomes magnetized, in a magnetic field and seeing how it lines up. So the direction of the field is the direction that the north pole of the dipole placed in the field will point. And after that, the rules for field lines are pretty similar. The density of field lines is proportional to the magnitude of the field. The direction of the field line is always tangent to the field line at any point when it's curved. So the big difference is electric field lines have sources, positive and negative charges where they begin and end. Magnetic field lines have no sources, no beginning and end. They're always closed loops, and they arise from moving charge. So when a moving charge or a current carrying wire is this way, the magnetic field lines are closed loops surrounding the wire. And so they begin and end on themselves. So those are the important differences between electric and magnetic fields. So the next three questions are pretty much the same question, and if we draw an electric dipole, we know what that looks like, but the difference is the field lines all leave the positive charge and go to the negative charge, and so they form a field that looks like this, symmetric on both sides. And that, a bar magnet, looks almost identical, only the difference is the field lines emerging from the North Pole go around to the South Pole and pass through the magnet and close on themselves. So from the outside, the shape of the field looks very similar. But if you look inside the magnet, the bar magnet, the field lines are closed loops. They have no beginning and no end. And so if you cut a bar magnet in half, you'll have two bar magnets, and no matter how thin you slice off the North Pole, you'll end up with a North Pole and a South Pole. And so as we think of electric charge as the source of electric field lines, we can think of moving electric charge or a current carrying wire or a free moving charge as the source of magnetic field lines. So that's not in the question, but I'm going to draw the current carrying wire and show you that. So if we're having a wire carrying current to the right, we know using right-hand rule number 2 that circular closed loops arise around the wire. It's a little hard to draw because it's three-dimensional, centered on the wire, and the direction given by right-hand rule number 2. So if I point my thumb in the direction to the right, you'll see that your fingers come out of the page here and go into the page there. And remember that if you want to represent a vector coming out of the page, you represent it by a dot, as if you're looking at the point of an arrow. And if you want to see it going into the page, if you want to show a vector going into the page, you're looking at the tail feathers of the arrow. And so on the upper side of the wire, all the field lines are coming out of the page, whereas down here they're all going into the page. And so the movement of electric charge is the source of the line, but the line doesn't emerge from the wire or the charge. It circles the wire in a closed loop. And so if we take this wire and bend it into a circle, or we make a loop out of the wire so that it goes around counterclockwise, and we use right-hand rule number 2, we can see that for this segment of wire, the field is coming out of the page here and going in there, and for this segment of wire, it's coming out of the screen here and into the screen there. And for the segment of wire going down, or any segment at all, we see all the field lines are coming out around the outside and going in on, coming out from the inside and going in around the outside. And if we rotate this out of the screen 90 degrees, we have a current carrying loop, which is a dipole. So since all the field lines are emerging from this front side, it means that we're looking at the north pole of a magnet. But if we went around to the back side of the screen, we'd see the field lines going around and entering. And so the other side of the loop would be the south pole. And so if we make multiple loops, then we add, each loop has current going in one side, a magnetic field going in one side and coming out the other side. And so the loop becomes the same field as a bar magnet. It becomes a magnetic dipole. And the shape is pretty much the same as the electric dipole, and the end of the coil from which the field lines emerge is what we would call the north pole, and the end of the magnet where the field lines enter, we would consider that the south pole. And notice the field lines bend this way as they go out and bend around and come back. And so if we put a bar magnet here, the north pole is going to be at this end and the south pole is going to be at that end, in the opposite direction of the coil producing the magnetic field. So a bar magnet and a coil of wire are both examples of a magnetic dipole, a single loop or many loops. And so you should be able to draw those and identify those and understand that fundamental difference between electric and magnetic field lines. So all that includes the bulk of what we need to know, or what we've learned this week. I didn't talk much about the right-hand rules, which is also important. What we need to know about magnetism, magnets, and magnetic field lines.